I'd like to show you how to work through a difficult problem associated with atmospheric air that's flowing through a heat exchanger. Atmospheric air, a mixture of dry air and water vapor. So let's go ahead and get started. This is problem 1236, and it turns out it looks easy, but it's a pretty difficult problem. So I've also created a video working out problem 1237, which is far easier. So if you're just getting started on these atmospheric air mixture problems, I suggest you look at the video for 1237 first, and then come back and work on this problem. So let's look and see what the problem statement is. Okay, it says air at 12 degrees C, a pressure of 1 atmosphere and 40% relative humidity enters a heat exchanger with a volumetric flow rate of 1 cubic meter per second. A separate stream of dry air enters at 280 degrees C, 1 atmosphere, with a mass flow rate of 0.875 kilograms per second, and exits at 220 degrees C. It says neglecting heat transfer between the heat exchanger and the surroundings, pressure drops of each stream, and no changes in kinetic and potential energy determine the temperature of the exiting moist air in degrees C. And then we've blotted out part B, which talks about the rate of exergy destruction. We don't even cover exergy in this course, so we're not going to work on part B. Okay, well, let's look for keywords and clues. It says air at 12 degrees C, 1 atmosphere, and 40% relative humidity. That's going to be a clue that you've got atmospheric air at a certain relative humidity. You've got a mixture, dry air and water vapor. Keyword heat exchanger. So I hope you've got experience now. When you see the word heat exchanger, that tells you that you've got two streams operating, that are two flowing streams, and they're exchanging energy with one or another. It says, let's see, dry air enters at 280, blah, blah, blah. Well, that tells you that one of the streams is dry air, and then it talks about with the 40% relative humidity, moist air is in the second stream. Okay, so let's see, heat exchanger, open system. You've got 2 inlets and 2 outlets. It does say the heat exchanger is fully insulated, is not exchanging heat with the surroundings. And also, your good common sense says the heat exchanger is not lifting a weight. There's no shaft coming out of the heat exchanger, so work or power is not involved. And so finally, you're asked simply to find the exit temperature of the moist air. Sounds pretty easy. You're going to find that it's pretty difficult to do this problem. Okay, let's start with a sketch. All right, so here's our basic sketch, a good simple way to describe what you've got. Certainly show this hot, dry air from state 1 to state 2 going through some vessel heat exchanger. The 2 streams don't mix. 3 to 4, that's going to be the atmospheric air and vapor mixture. Within the heat exchanger, heat's being exchanged between the 2 streams, but you see that I've shown this insulation such that this heat exchanger vessel is not exchanging heat with the surroundings. So that's really a pretty good sketch, pretty good way to get started. Now, if you are not familiar with mixtures, I want to suggest that you go to my YouTube channel and find the playlist example problem psychrometrics and Atmos-Air 01. That's atmospheric air video 1. Really covers the basics, and I think it would help you to at least browse that video if you need some background in dealing with these mixtures, air, dry air, and vapor. All right, there's 2 approaches to solving this problem, and I'd like to review both of them, even though we're going to use a second approach. So approach number 1, we are not going to use this approach. we've got an open system, steady state, steady flow. One stream is moist air, one stream is dry air. And I've drawn my control surface around the entire heat exchanger vessel or equipment. And so do you see then that if I took this approach, I'd write the first law for this open system. I'd say Q dot into the heat exchanger, that's nothing, minus W dot out of the heat exchanger, that's nothing, equals the sum of the M dot leaving H leaving minus the sum of the M dot in H in. And so you could simplify this to say you've got M dot 1 times H2 minus H1 plus M dot 3 times H4 minus H3. So okay, so I think you've got that. We're not going to take that approach. Here's the approach we will take. And we're going to still have two open systems. And we're going to treat both of them as steady state, steady flow. And my remark here on the right is, I find this approach, even in engineering practice, it's easier for me to go step by step to solve this problem. And for that reason, it's easier for me to understand. So let's look at my sketch for this approach number 2 and see where we go from here. So here is going to be one of my open systems, the hot, dry air, one inlet and one outlet. And there is heat transfer involved from the hot air into somewhere else. Okay, so there's sort of one sketch. My next sketch included is one inlet, one outlet, steady state, steady flow of the moist air mixture coming in at 12 degrees C and leaving at some unknown temperature, but at least you know it's going to be greater than 12 degrees C because heat is being exchanged from the hot, dry air coming in at 280 and leaving at 260. So your common sense sort of agrees with this sketch. So let's write the first law. When we don't know where to start, let's write the first law for each of these open systems. Okay, so for the hot, dry air, Q into the hot, dry air, well, we know it's going to be a negative number, minus W dot, that's 0, not lifting the weight, equals M dot 1 times H2 minus H1, because the M dot 1 equals M dot 2, of course, steady flow. So that's a pretty simple statement of the first law for our hot, dry air. For the moist air, Q dot into the moist air, that certainly common sense says it's going to be a positive number, minus W dot out, that's 0, not lifting weight, equals M dot 3 times H4 minus H3. So at least we've got our first laws written down, and we can observe that Q dot into the moist air must exactly equal Q dot minus Q dot into the hot, dry air, or in other words, Q dot leaving the hot, dry air. So Common Sense 101 tells you that because that's where the energy is flowing from hot to cold in this heat exchanger. So at least we've got a start. Okay. So if we've got, now I'm going to try to work you through, before we start putting numbers down, even on the video, let's plan our work. And so I am going to try to show you that the solution approach is pretty involved. Note slide 1 of 6 slides coming up. So let's work on the hot, dry air stream first. So here's my sketch for my hot, dry air stream. Okay, so you see the given information, written it down. Let's write down the first law to solve for the heat transfer into the hot, dry air. You know it's going to be a negative number, so let's just bang through that. Let's also model the dry air as an ideal gas with constant specific heat. And the reason for that, the reason we can say that we model this hot, dry air with constant specific heat is because, look, the temperature is not changing. In the whole scheme of things, the temperature is only changing by 20 degrees C. That's not a great deal of change. And so we're well allowed to, for this problem, to model the air with constant specific heat. So let's write the first law. Q dot into the hot, dry air minus W dot out, that's going to be 0, is equal to M dot 1 times H2 minus H1. Let's keep going. Let's look at some details. M dot 1 integral. What's the change in enthalpy? It's the integral from 1 to 2 of Cp dt. Oh, we've said Cp is constant. We'll pull Cp out of the integral. So we'll simplify. We've got m dot 1 times C sub p times T2 minus T1. Now let's see what we know. Can we solve immediately for Q dot into the hot, dry air? M dot given, Cp. We've got to look that up. Okay, T2 minus T1 both given. This looks like it's going to be pretty easy. So now we're going to move on. Okay. We're not going to do that numerical work. We're going to save that for later. Now, slide 2 for the setup for planning our work. Let's move over and, oh, I see I've got a typo already. Let's work on the moist air mixture stream 3 to 4. Look at that, I put 1 to 2. It's 3 to 4. Okay, so here's my sketch. At least my sketch is correct. Okay. And let's review our fundamentals of this sketch. Review the fundamentals. You certainly would agree that m dot, let's look at the m dot of the dry air, mass flow of the dry air. Common Sense 101 says the dry air flow coming in must exactly equal the dry flow airflow coming out. And similarly, we've got a mixture. There's mass flow of vapor coming in and mass flow of vapor coming out. There's nowhere else for it to go. So m dot 3 of the vapor's got to equal m dot 4 of the vapor. Let's simplify our nomenclature as we solve the problem. So m dot 3 of the dry air equals m dot 4 of the dry air, and let's just call that m dot of the dry air. Similarly for the vapor, m dot 3 of the vapor exactly equals m dot 4 of the vapor. Let's just call that m dot of the vapor. So we've got 2 m dots to worry about at states 3 and 4. Okay. Another memory refresher, omega, the heat, the humidity ratio, Greek letter omega, it's m dot of the vapor divided by m dot of the dry air. And so look, since these things are constant, these mass flows are constant, we can observe that omega 3 equals omega 4. So that's a key thing to write down and recognize. Let's keep plugging ahead for what are we going to need to do? Let's remember back about the first law. We're going to need m dot of the dry air. We're not given m dot of the dry air. We only have the volumetric flow rate of the mixture given, 1 cubic meters per second. So that's AV, isn't it? Area times velocity. AV3 is given. So we've got to use that to figure out m dot of the dry air. How will we do that? Well, m dot is going to be the volumetric flow rate divided by specific volume. So we've got to figure out the specific volume of the dry air, little v3 of the dry air. We got to figure that out. How are we going to do that? It's going to be the next slide. And so we'll solve, once we find little v3 of the dry air, we'll be able to solve immediately for m dot of the dry air. Okay. Next thing we got to do is work on V3 of the dry air. Wow. Ideal gas equation of state. That involves little v, doesn't it? So let's write that down. The partial pressure of the dry air times the specific volume of the dry air equals R of the dry air times T. Well, we've got T3, okay? R. We can, well, here it is. R of air is going to be R bar over the molecular weight, or 0.287. Hopefully you've got that in your head. You've memorized that. And T3's got to be in absolute temperature, so that's 285 degrees K. So I think you see that you can immediately calculate, you need P3 of the dry air. You can't immediately calculate. How are we going to get the partial pressure of the dry air? We still don't have specific volume yet. Well, we got to think about how can I get the partial pressure P3 of the dry air? I know that I'm given the relative humidity at state 3. It's 40%. Phi3, Greek letter phi, Phi3 is 40%. What's that defined as? That's the partial pressure of the vapor divided by saturation pressure of the vapor, PG, at T3. Well, we can look up PG. We can look that up. So if we look up P sub G in the steam tables, temperature table, we can solve for P3 of the vapor. Whew. Well, that's not what we're looking for. We're looking for P3 of the dry air. So we have to remember the definition of that's going to be P of the system, 1 atmosphere, given minus P3 of the vapor that we just found. So we're going to put in, well, we're here in the slide, it says 101. We're going to put in 101.325 kPa minus P3 of the vapor to solve for P3 of the vapor. And so this is sort of a neat, you might not think it's so neat, but anyway, it is an observation about solving thermo problems. Is do you see that we've gone down the path and probably gotten a little confused, but you see you're backing up. You think through all these things, and you in your solution, you've got to back up. You've got to start here and work backwards to get m dot of the dry air. So that can be a real confounding part of thermodynamics class, but it's a skill that you've got to master. So we're backing up to find m dot of the dry air with all of these computational details. And that's only slide 3 of 6. Okay, so let's continue on. We're trying to find T4. That's what we're trying to find is T4. Well, let's write the first law. Again, when you're stuck, write the first law, and that can generally help you. So let's write down for process 3 to 4, open system, steady state, steady flow, one inlet, one outlet. First law, Q dot in. Well, we will have found that. That's from the other flow stream. Minus W dot out, that's 0. M dot 3 minus M dot 3 times H4 minus H3. That's kind of complex, isn't it? Because you've got two substances at 3 and 4. You've got dry air and you've got vapor. So let's split that out. H4 minus H3. So we've got M dot of the dry air times H4 minus H3 of the dry air plus the vapor. M dot of the vapor times H4 of the vapor minus H3 of the vapor. That's going to be key. This could be a place that you pause this you pause this video and you kind of jot that down. Now for the dry air, CP was constant, so let's continue to write down a new equation. Let's simplify. Let's drop out the work term, the power term. Q dot into the moist air, we've already found that. We'll have found that. And so we've got M dot of the dry air. We found that. CP of the air, we need to look that up. We will have already found that. CP of the air times delta T of the air. T3 we know, T4 we don't know. And then our trailing term, M dot of the vapor times H4 of the vapor minus H3. Okay, and so remember, well, what's M dot of the vapor? Oh, how are we going to get that? We remember that M dot of the vapor is simply omega, the humidity ratio, times M dot of the dry air. And I'll chase you back to your textbook, give you some reminders. How do you get omega? Well, that's from the textbook. It is this fundamental, involves molecular weight ratios and some partial pressure ratios. A little more about that in a second. Okay, we've gotten through slide 4 of 6 on setting up our problem. All right, we're continuing on with the first law. Let's see. So we've got, this is just from the previous slide, okay? What I want to do is simplify where I can. Do you see the M dot of the dry air, CP of the air, delta T? Let us substitute omega times M dot of the dry air for M dot of the vapor to try to simplify things down. Okay, so that's just a simplification that we wrote down on the previous slide. M dot of the vapor is omega, humidity ratio, times M dot of the dry air. Now let's see. I've got an M dot of the dry air that I can collect from my two terms. And so here it is. Here's the left-hand side, Q dot in. M dot of the dry air times the quantity, CP of the air times T4 minus T3, plus omega times H4 of the vapor minus H3. And now let's start checking off things we have found in our computational work. Q dot in, we got it. M dot of the dry air, we have it. Cp of the air, we will have looked that up. T4, we don't know. That's what we got to find. T3, we know. Omega, we will have determined that. H4 of the vapor, well, gosh, H4 of the vapor depends on T4, so that's still a question mark. Darn it. H3 of the vapor, we've got that. That's simply going to be Hg at T3. So we've got a lot of checks, but we've got 2 question marks. So we got to still try to see if we can get down to, how do we get to 1 equation and 1 unknown? All right. Still gets tough. So I've written down this from the previous slide. And what I want to suggest is we set up a single equation where the left-hand side equals 0. So all I'm going to do is subtract Q dot N from both sides to get this relationship. 0 equals M dot of the dry air. Oops, I didn't put a dot over M dot of the dry air. It's a typo. There's my dot. I need to move it to the left. Cp of the air, delta T, plus omega, H4 minus H3 of the vapor, minus Q dot into the moist air. So now, this is our computational setup. It says it remains. So I've got 2 variables here that depend on T4. Okay. Here's what it remains to do. And this is why this is such a tough problem. It remains to guess T4. Once you've guessed T4, you have to figure out what is H4 of the vapor from the steam tables, and then systematically keep guessing until the right-hand side of this equation exactly equals 0. So that makes this a tough problem, even with all the details of setting the problem up. So this is a tough one. Some quick reminders of how I got those fundamentals as I work through the setup, and then we're going to get into the numerics of this problem. Example 1210 is a good example of heating moist air in a duct. So you see how that's similar to this problem, and this is how we get the mass flow rate of the dry air right out of your textbook, and also the specific volume of the dry air. So I'll try to chase you back to your textbook. Study on example 1210 to help yourself out. Okay. Where did I get the humidity ratio? Well, that's equation 1243, and the textbook does a very nice job. Instead of just giving you a formula, this formula can be derived from fundamentals. Okay, so that's where we get the expression for Greek letter omega. Okay, and notice here, the numerator for this P, that's the partial pressure of the vapor. The denominator is P minus PV. Well, P in the textbook is what I call P of the system, P sys, okay? Or in our case, it's 1 atmosphere, okay? And so it's the partial pressure of the dry air is P of the system minus PV. So that denominator is the partial pressure of the dry air. Okay, I think last in your book is looking up the enthalpy of the vapor in this mixture, H sub V, HV3, HV4. And here, the textbook does a nice job of explaining why and how you look up H sub V out of the steam tables in the temperature table. Okay, and so now finally, we're able to start the numerics of our solution. It took a lot of thinking. It took a lot of planning. Now we're ready to put pencil to paper. Okay, and so I'm going to work on process 1 to 2 first, the dry air, and the purpose for that is getting the heat transfer, well, into the dry air. It's going to be a negative number. So I've written down my 2 temperatures. I've changed them to degrees K, okay, and there's a reason to do that. And let's see, M dot of the dry air is given 0.875 kilograms per second. I need to get degrees K because I've got to look up in table A20 to determine a constant value for C sub P. And so I'm looking around, 500 to 550. And I got to tell you, I'm just eyeballing it. I'm not doing a detailed interpolation. In my solution, I'm writing down C sub P is 1.03. Okay, so just to save time and to move on to important things, C sub P is 1.03. And R, I remembered off the top of my head, I didn't have to do R bar with the molecular weight because I've got R for dry air is 0.287 kilojoules per kilogram degree K. So now it's plug and chug, right? So plug and chug into the first law to get Q dot into the hot dry air is negative 54.075 kilowatts. Kilojoules per second equals kilowatts. And so therefore, based on our study, Q dot into the moist air, 3 to 4, is the negative of that, or plus 54.075 kilowatts. So at least we've got some partial credit. At least we have figured out how much heat is flowing from the hot dry air stream into the mixture, the atmospheric air mixture stream. At least we've got that. Okay, the next thing is we're going to find the partial pressure of the vapor at state 3 because we've got to find the humidity ratio omega. And we need that to find m dot of the dry air. So what we're working towards here is m dot of the dry air. So we need the partial pressure of the dry air to get the to get the specific volume of the dry air. That's where not omega. So anyway, let's do our work. So we're going to go to the temperature table at 12 degrees C. 0.014 bars is PG3. Okay, that's the saturation pressure of the mixture, of the vapor mixture at T3. 1.402 kPa. Okay, what's the partial pressure of the vapor? PV3 is the relative humidity, 0.4 times PG3. And so that's going to be 0.5608 kPa. So that's PV3. But we need the partial pressure of the air. Okay, so now we'll find partial pressure of the air. Okay, so this is my Excel version of what I just showed you on the previous slide, 40% relative humidity. I wrote down that PG3 is 1.402 kPa from the table, and then I did my math to get PV3 is 0.5608 kPa. So I also wrote down the pressure of the system, P3, PSYS, 101.325. I didn't remember that off the top of my head. I went to our book to get 1 atmosphere is 101.325 kPa. Typically, it's okay to write 101, but I wrote 101.325. And so now I can subtract this amount from this big amount to get the partial pressure of the dry air, P3 sub A, is 100.764. Ooh, wow. So now what was I trying to do in the first place? I'm trying to get specific volume of the dry air. Here we go. All right. I've written down R for air, T3 in degrees K. I just found the partial pressure of the dry air. So now I can use the ideal gas equation or state to get the specific volume of the dry air. 0.81175 cubic meters per kilogram. It's state 3. Specific volume of the dry air. So therefore, I was given AV3, the volumetric flow of the mixture. So now I can, so from the textbook guidance, m dot of the dry air is the volumetric flow of the mixture divided by V3 of the dry air, a little specific volume of the dry air. Whew, so now I've got a little more partial credit. The mass flow of the dry air is 1.232 kilograms per second. Wow. So I've gained a little more partial credit. This is kind of helping me gain partial credit, even if I don't get to the end of this problem. Okay. The humidity ratio. I'm thinking back about my first law, about that one equation I've got to solve for. So I need the humidity ratio, omega. Well, I've calculated everything. PV3 from previous work, 0.5608. The partial pressure of the ingoing mixture, 101.325, that's 1 atmosphere. So I'll apply what I've got here. Omega is 0.622, PV over partial pressure of dry air, P minus PV. Humidity ratio is 0.003462 kilograms of vapor per kilogram of dry air, a small, tiny number. Kilograms of vapor per kilogram of dry air. So we're going to need that to fully solve the problem. But I do have a little more partial credit this way. All right, so now we're going to go about solving our zero equals equation. So I've written it back down. Zero equals m dot of the dry air. Darn it, I still need to move that dot over to the left. Sorry. Cp of air, we've got it. T4 minus T4, don't have it. T3, got it. Omega, have it. H4 the vapor, we need that, but we can't get it until we guess T4. H3 the vapor, we have that. And Q dot into the moist air, that is found. We have that. Okay, so we got to start guessing. Got to start guessing T4. Now, I had to do some guessing and I had to hone in on it. So I'm gonna show you some of my guesses to get to it. So I'm going to show you my guess at 55 degrees C and go through the numbers associated with that. At 55 degrees C, gosh, I don't have a 55 in my temperature table. I've got to interpolate between 55 and 65. Well, it's 2600.9. Okay, the interpolation is 2600.9. Okay, so I've got H4 of the vapor at 55. Okay, got it. So I can run, and T4, I just guessed, 55 degrees C. So I can run through my numbers and evaluate this right-hand side, and it's not zero. It's negative 0.507. So my guess of 55 degrees is not a solution. So let's guess again. So let's guess higher. 65. All right, well, in my temperature table, I've got, at 65, I've got H sub 4 of the vapor is 2618. So I'll put that in there, okay? And T4 I just guessed, okay? And I'll evaluate the right-hand side, and I get 11.947. That's still not zero. I got to keep guessing. Now, you see that I do solve my homework problems just like I did in engineering practice in engineering problems in Excel, okay? So the next thing I did was I used the Excel goal seek tool where I'm trying to set the right-hand side of this equation equal to zero by setting the right-hand side equal to zero. So I'm trying to force the right-hand side to be zero by guessing T4. And I use this goal seek tool then to change this blue cell in Excel. And then Excel found for me the interpolated value for HG between 55 and 65. And so Excel is doing all this mathematics, let's say hundreds of times, to hone in on 55.41 gives the right-hand side equal to zero. So you can see here, we go through the math, the right-hand side is 0.0. So at least to the third decimal place, we've got a result of 0 equals 0. So I have determined my solution. The final result is that T4 is 55.4 degrees C. Wow, that is involved. This is clearly a problem that would not be a quiz question. It would not be a test or exam question. But do you see that if you work on this problem, you're going to learn a huge amount of fundamentals that will help you in the quiz and test and exam problems. So let's see. So that's it. I have clearly shown my result, T455.4. What did we learn from this extraordinarily difficult problem? You got to start with a sketch. We had several sketches. You have to plan your work because this and start with fundamentals, because this was clearly a problem where you had to back into the solution. If you were given all these little formulas, you could turn the crank and do that. But in engineering, nobody gives you all the little formulas for you to work through. That's what we do for technicians. So backing into the solution, this is a classic example of having to think through the problem, think through the fundamentals, back in the solution. And so you see that blindly using formulas for homework solutions, that's not going to help you on quizzes and tests. And also, you'll see that in my solution, I had my units, I stated my units throughout the solution. Okay, tough problem. I appreciate your hanging in there. The next video I've prepared is the solution to the exact same problem, except I want to show you how to use the psychrometric chart to your advantage to make the numerical solution just sail through. The fundamentals are the same, but the psychrometric chart helps you sail through this problem much, much quicker and not do a guess T4 and solve and re-guess and solve and re-guess and solve. Okay, a couple of typos, a couple of dots in the wrong places, but I hope this has helped you see some fundamentals about air and vapor mixtures, atmospheric air that we deal with all the time, particularly in heating, ventilating, and air conditioning, and hope it helps you see how to work through an extremely complex problem.